Hello there, Steve here. Welcome back to another Sleepy Steve story. Before we drift off tonight, remember to subscribe to help Steve-O out, and I will keep making more sleepy stories to help you study gently, revise quietly, and settle your mind at the end of the day. Tonight, we are moving into Unit 3 Chemistry. That means the story becomes a little more direct, a little more exam-focused, and a little more connected to how chemists use evidence, calculations, and design choices to solve real problems. But we are still going to take it slowly. The room is still quiet. The voice is still calm. And the ideas will still arrive one at a time. This episode begins Unit 3, Area of Study 1, and we are thinking about fuels, combustion, and energy options. You might picture a quiet science classroom late in the afternoon. The benches have been cleaned. The gas taps are turned off. A small model of a methane molecule sits near the front desk. On one side of the room, there is a simple diagram of a petrol engine. On another wall, there is a picture of a wind farm, a solar panel, a biofuel crop, and a hydrogen fuel cell. Outside the window, the school car park is almost empty. A bus moves slowly away from the curb. A few streetlights begin to glow, and somewhere in the distance, energy is being transformed. Chemical energy becomes heat. Heat becomes movement. Light becomes electricity. Electricity becomes motion, sound, warmth, and work. Chemistry helps us understand these changes. It helps us ask where energy comes from, how efficiently it can be used, and what effects it has on people and the environment. So take a slow breath in and a slow breath out. Let the classroom become still. Let the small model of methane rest quietly on the bench. And let's begin with the idea of a fuel. A fuel is a substance that can release energy when it reacts. Most of the fuels we use contain stored chemical energy. That chemical energy is held in the bonds between atoms. When a fuel reacts, old bonds are broken, new bonds are formed, and energy is transferred to the surroundings. In many everyday situations, a fuel reacts with oxygen in a combustion reaction. Combustion is a reaction with oxygen that releases energy, usually as heat and often as light. When a candle burns, combustion is occurring. When petrol burns in a car engine, combustion is occurring. When natural gas burns in a stove or heater, combustion is occurring. When wood burns in a fireplace, combustion is occurring. These examples may look different, but the chemical pattern is similar. A fuel reacts with oxygen. Energy is released. Products are formed. If the fuel contains carbon and hydrogen, complete combustion usually produces carbon dioxide and water. For example, methane is the main component of natural gas. Methane has the formula CH4. When methane undergoes complete combustion, it reacts with oxygen to produce carbon dioxide and water. The balanced equation is methane plus oxygen produces carbon dioxide and water. One methane molecule reacts with two oxygen molecules to produce one carbon dioxide molecule and two water molecules. In symbols, CH4 plus 2O2 produces CO2 plus 2H2O. This equation is small, but it carries many important ideas. It shows that atoms are conserved. One carbon atom on the reactant side becomes one carbon atom in carbon dioxide. 4 hydrogen atoms become 4 hydrogen atoms in 2 water molecules. 4 oxygen atoms in 2 oxygen molecules become 2 oxygen atoms in carbon dioxide and 2 oxygen atoms in water. The atoms are not created or destroyed, they are rearranged. And as they rearrange, energy is released. In Unit 3 Chemistry, you need to be comfortable moving between the chemical equation and the story it tells. A fuel reacts. Oxygen is consumed. Products form. Energy is transferred. And if carbon dioxide is produced, there are environmental consequences to consider. Now let's think about fossil fuels. Fossil fuels include coal, crude oil, and natural gas. They formed over millions of years from the remains of ancient living things. Coal mainly comes from ancient plant material. Crude oil and natural gas formed from ancient marine organisms under heat and pressure over very long periods of time. Because they take so long to form, fossil fuels are considered non-renewable on a human timescale. They can be used much faster than they are naturally replaced. Fossil fuels have been important because they are energy dense. That means they can release a large amount of energy from a relatively small mass or volume of fuel. They are also transportable and have been supported by large existing infrastructure. Cars, power stations, ships, aircraft, factories, and heating systems have all been built around the use of fossil fuels. This is one reason change is difficult. Chemistry is not only about whether a reaction can release energy. It is also about cost, availability, storage, safety, infrastructure, efficiency, and environmental impact. Coal is often used to generate electricity. In a coal-fired power station, coal is burned to release heat. The heat is used to boil water and produce steam. The steam turns a turbine. The turbine drives a generator. Chemical energy in coal is transformed through several steps into electrical energy, but each step involves energy losses. Some energy is transferred to the surroundings as waste heat, and the combustion of coal produces carbon dioxide as well as other pollutants depending on the fuel and conditions. Crude oil is a mixture of hydrocarbons. A hydrocarbon is a compound containing only carbon and hydrogen. Crude oil can be separated into fractions through fractional distillation. Different fractions contain molecules with different chain lengths, boiling points, and uses. Petrol, diesel, kerosene, and lubricating oils all come from crude oil fractions. The shorter hydrocarbon chains tend to be more volatile and easier to ignite. The longer chains tend to have higher boiling points and are less volatile. This links back to structure and properties. The size and shape of molecules influence intermolecular forces. Intermolecular forces influence boiling point. Boiling point influences how the substance can be separated and used. Natural gas is mainly methane. It is often described as a cleaner fossil fuel than coal because it generally produces less carbon dioxide per unit of energy released. But it is still a fossil fuel. Its combustion still produces carbon dioxide, and methane itself is a powerful greenhouse gas if it leaks before being burned. So a strong chemistry answer should be careful. It should not simply say that natural gas is clean. It is better to say that natural gas may produce fewer carbon dioxide emissions than coal for the same amount of energy. but it still contributes to greenhouse gas emissions and must be considered in terms of extraction, leakage, transport, and overall life cycle impact. That is more precise. That is the kind of careful comparison Unit 3 rewards. Now, let's think more closely about complete and incomplete combustion. Complete combustion occurs when there is enough oxygen available for the fuel to react fully. For a hydrocarbon fuel, complete combustion produces carbon dioxide and water. Incomplete combustion occurs when there is limited oxygen. Instead of producing only carbon dioxide and water, incomplete combustion can produce carbon monoxide, carbon particles, sometimes called soot, and water. Carbon monoxide is dangerous because it binds strongly to hemoglobin in the blood, reducing the ability of blood to carry oxygen. Soot is also a problem because small particles can contribute to air pollution and affect respiratory health. Incomplete combustion also means the fuel has not released as much useful energy as it could through complete combustion. In a quiet laboratory explanation, you might imagine two flames. One flame burns with a steady blue color with good oxygen supply. Another flame is yellow and smoky, with less oxygen available. The smoky flame is a sign that combustion is less complete. In an exam response, if you are comparing complete and incomplete combustion, include the oxygen availability and the products. Complete combustion has sufficient oxygen and produces carbon dioxide and water. Incomplete combustion has limited oxygen and may produce carbon monoxide, carbon, and water. That simple distinction is important. Now let's move from fossil fuels to biofuels. A biofuel is a fuel produced from biomass, which is material from recently living organisms. Examples include ethanol made from plant sugars, biodiesel made from vegetable oils or animal fats, and biogas produced from the breakdown of organic waste. Biofuels are often described as renewable because the plants or organic materials used to produce them can be regrown or replaced over a shorter period of time. But again, chemistry needs careful language. Renewable does not automatically mean impact-free. Biofuels still involve land use, water use, fertilizers, harvesting, processing, transport, and combustion. They may reduce reliance on fossil fuels. They may support energy security. They may be produced from waste materials, but they may also compete with food production or contribute to environmental pressure if not managed carefully. Ethanol is a useful example. Ethanol has the formula C2H5OH. It can be produced by fermentation of sugars. In fermentation, glucose is converted into ethanol and carbon dioxide, usually with the help of yeast. The ethanol can then be used as a fuel or blended with petrol. When ethanol undergoes complete combustion, it produces carbon dioxide and water, releasing energy. So even a biofuel can release carbon dioxide when burned. The reason biofuels may be considered lower impact is connected to the carbon cycle. The plants used to make the biofuel absorbed carbon dioxide from the atmosphere during photosynthesis. When the fuel is burned, carbon dioxide is returned to the atmosphere. This can be closer to a short-term carbon cycle than fossil fuels, which release carbon that has been stored underground for millions of years. But the total environmental impact depends on the whole production and use pathway. That is why the phrase carbon neutral should be used cautiously. A biofuel may be more sustainable than a fossil fuel in some contexts, but it is not automatically carbon neutral once farming, processing, and transport are included. Now let's think about energy options more broadly. A fuel is one way to supply energy, but not all energy options involve combustion. Solar panels convert light energy from the sun into electrical energy. Wind turbines convert the kinetic energy of moving air into electrical energy. Hydroelectric systems use moving water to turn turbines. Batteries store chemical energy and convert it into electrical energy through electrochemical reactions. Fuel cells convert chemical energy into electrical energy more directly than combustion engines. Each option has strengths and limitations. Solar energy is renewable and does not produce carbon dioxide during operation, but it depends on sunlight and requires materials, manufacturing, and storage solutions. Wind energy is renewable and low emission during operation, but it depends on wind conditions and suitable locations. Hydroelectricity can produce large amounts of electricity, but it can affect rivers, ecosystems, and communities. Batteries can store energy and support electric vehicles and renewable electricity systems, but they require materials such as lithium, nickel, cobalt, or other metals, and their production and recycling need to be considered. Fuel cells can produce electricity from fuels such as hydrogen, often with water as the product if hydrogen and oxygen are used. But hydrogen must be produced, stored, and transported, and the sustainability of hydrogen depends strongly on how it is made. Chemistry helps us compare these options by asking precise questions. What is the energy source? What energy transformations occur? What substances are consumed? What products are formed? How much useful energy is obtained? What emissions are produced? What resources are required? How sustainable is the system over its full life cycle? This is where Unit 3 chemistry becomes more than memorizing fuels. It becomes a way of evaluating choices. A petrol car, an electric car, a hydrogen fuel cell vehicle, and a bus using biodiesel all involve different energy pathways. They may all help people move from place to place, but the chemistry underneath them is different. The emissions are different. The infrastructure is different. The efficiency is different. And the sustainability depends on more than the final vehicle. It depends on where the fuel or electricity came from. Now let's introduce the idea of energy transformations. Energy cannot be created or destroyed. It is transformed from one form into another. In combustion, chemical energy stored in the fuel is transformed mainly into thermal energy. That thermal energy may then be used to produce mechanical energy, as in an engine, or electrical energy, as in a power station. But no energy conversion is perfectly efficient. Some energy is always dissipated to the surroundings, often as heat. Efficiency describes how much of the input energy is converted into useful output energy. For example, in a car engine, not all the chemical energy in petrol becomes useful kinetic energy of the car. A large amount is lost as heat and sound. This matters because a fuel may contain a lot of chemical energy, but the final useful energy depends on the efficiency of the system using it. So when comparing energy options, do not only ask how much energy the fuel contains, also ask how efficiently that energy can be converted into useful work. This is a key habit in Unit 3. Energy content and energy efficiency are related, but they are not the same thing. Now, let's think about how chemists compare fuels. One useful measure is energy released per gram or per mole. Another is energy released per volume, especially for transport fuels. Chemists may also compare carbon dioxide produced per unit of energy released. A fuel that releases a large amount of energy but also produces high carbon dioxide emissions may be less desirable in a low-emissions energy system. A fuel that produces fewer emissions but is difficult to store or transport may have other limitations. A fuel that is renewable but competes with food crops may raise social and environmental questions. So the comparison is not one-dimensional, it is a balancing act. Energy density, emissions, cost, safety, reliability, storage, renewability, infrastructure, environmental impact, social impact. These are all part of evaluating energy options. You do not need to solve all of the world's energy problems in one chemistry answer, but you do need to show that you can use chemical knowledge to make a reasoned comparison. For example, you might say that petrol is energy dense and easy to transport using existing infrastructure, but its combustion releases carbon dioxide and contributes to greenhouse gas emissions. You might say that ethanol can be produced from renewable biomass and used in existing fuel blends, but its sustainability depends on land use, agricultural inputs, and production methods. You might say that hydrogen used in a fuel cell can produce electricity with water as the main product, but the environmental impact depends on how the hydrogen is produced. These are balanced, careful statements. They show chemistry thinking. Now let's connect this to greenhouse gases. Carbon dioxide is a greenhouse gas. It can absorb and re-emit infrared radiation, contributing to the greenhouse effect. The greenhouse effect is a natural process that helps keep Earth warm enough for life. The concern is the enhanced greenhouse effect, where increased concentrations of greenhouse gases from human activities lead to additional warming. Combustion of fossil fuels has contributed significantly to increased carbon dioxide concentrations in the atmosphere. This links energy choices to climate change. In chemistry, we do not only say that burning fuels is bad, we explain the chemical reason. Carbon-containing fuels react with oxygen. Carbon atoms in the fuel are converted into carbon dioxide. Carbon dioxide accumulates in the atmosphere when emissions exceed natural removal processes. This changes the balance of Earth's energy system. That is a chemical explanation with environmental significance. Now, let's return to the quiet classroom. The model of methane is still on the bench. The diagrams on the wall are still there. Coal, oil, natural gas, biofuel, solar, wind, batteries, fuel cells. Each one represents a way people try to meet energy needs. Each one involves chemical or physical processes. Each one has benefits and limitations. And in Unit 3 Chemistry, your task is to understand enough of the chemistry to evaluate those options clearly. A strong exam response might begin with the fuel or energy source. Then identify the key reaction or energy transformation. Then describe the products or emissions. Then compare benefits and limitations using chemical reasoning. For combustion of a hydrocarbon, remember the simple pattern: fuel plus oxygen, carbon dioxide plus water, energy released. For incomplete combustion, remember the limited oxygen, carbon monoxide, carbon particles. Less efficient energy release. For fossil fuels, Remember high energy density and established infrastructure, but non-renewability and greenhouse gas emissions. For biofuels, remember renewable biomass and potential lower net emissions, but also land use, processing, and life cycle impacts. For non-combustion energy options, remember that sustainability depends on the source, storage, materials, efficiency, and full life cycle. So tonight's idea can settle like this. Energy is not just something we use, it is something we transform. A fuel is not just something that burns, it is a store of chemical energy. Combustion is not just flame, it is atoms rearranging with oxygen, forming products, and releasing energy. And sustainability is not a single label. It is a careful comparison of resources, reactions, products, efficiency, emissions, and consequences. Let the classroom become quieter now. Let the diagrams fade softly in the evening light. Let the methane model sit still on the bench. And remember the calm pattern of the episode. Fuels store chemical energy. Combustion releases that energy. Complete combustion produces carbon dioxide and water. Incomplete combustion can produce carbon monoxide and soot. Fossil fuels are energy-dense but non-renewable and emissions-producing. Biofuels come from recent biomass but must still be evaluated carefully. And every energy option involves trade-offs. This is Unit 3 Chemistry beginning to ask its larger question. How can design and innovation help us optimize chemical processes? The first answer is simple. We need to understand the chemistry of energy before we can improve the way we use it. Sleep well, and let the energy settle quietly in your mind.